feel free to turn on the microphones and, interact, speak, ask questions, and anything else. So, just a second. So let's see. So today we're going to talk about two-pointer, binary search on static window, and binary search on the answer. Some, let's say, fundamental topics that may appear a lot. Just a second. So let's see. Let's start with two pointers. Let's say we have a problem saying, like, we have an array with some numbers, and then we have to find, for example, if, like, it also gives like some x number, and then we have to find answer if there is some pair of e.g. indexes that ae plus ag is equal to x. Any idea? For example, like how we could solve this? Today we don't really have people like in person, so it's just the Zoom. For example, Duman, any idea?
Can you repeat again?
Hello? Okay, so basically, can you repeat the statement? So yeah, very, very simple statement again. We have like an array A, right, with n elements, and then we are also given an x, some random number, and we have to find if we have a pair of two numbers somewhere in the array that the sum of those is equal to x. Any. Not necessarily something smart. There's nothing smart.
You can try something below.
I can hear. I think it's because of
And use X. Excuse me.
Sorry. Can you repeat? Start from the beginning. Like my laptop was connected to another speaker. Yep.
Try something brutal.
Brute force, right?
Yeah. Find a number and use X to minus that number, and then find a number in the list that equals to the sum we got.
So basically, if it's just a random array, right? We can't really do anything smart here because we just have to, for example, I don't know, let's say just nested four, like fix E, fix G, and then check if equal to X, that's it, right? And this is like O(n) square, right? But let's say if we had like the array sorted, right? for example, the array is like in the increasing order, what changes? Like, is there something that we can do? Yes, as Duman said over here, sliding window. So, or another thing which is called like 2 pointers, a similar thing. Let's say we have like initially 2 indexes, right? 2 points, which is like at the start and then at the end. One is, let's say, L equal to 0 and R equal to n minus 1, right? So, and if the array A is sorted in increasing like order, we don't really, basically, like, for example, let's say L plus R equals some sum. If we move the L to the right, it's going to, let's say, L1 plus R equals some 1. And then because L is smaller than small equal to L1, we get sum small equal to sum 1, right? We, by moving L to the right, we increase the sum, right? Or at least it's the same, basically. And then by moving the R to the left, because it's increasing order, it's sorted, right? We get L plus R equals sum, and then L plus R1 equals sum 1, and then basically R is more than R1, more equal, then sum is more equal to sum 1, right? Greater than equal. So what we see is that L moving right is increasing the sum, and then R moving left is decreasing it, right? So here what we can do is we can start from like this side and this side, right? Like L equal to 0 and R equal to n minus 1. And what we can do is we can just basically, like, step by step compare, like, let's say, get the sum, right? And then check if the sum is greater, if it's equal to x, right? We already found our answer, right? If the sum is greater than x, it means we need to get the sum lower, right? So we have to move R to left, right? And then if the sum is lower than x, we have to move, we have to get the sum like bigger, right? So we have to move L to right. Right? And then step by step, like, we just repeat it, like, well, L is like less than R, and then if we get somewhere this condition, we found it, and then otherwise there is nothing to search for. Basically, we get the answer, right? It was an example of sliding, no, sorry, 2 pointers. As we can see here, we can sort out the array, right? It will take like n log n. And then after, we just have the L and R, and then while L is less than R, we get the sum, and then we check. If the sum is equal to x, we break because we already found our answer. Otherwise, we check if the sum is less than x, L plus plus, otherwise R minus minus to get the sum lower. And then this part only takes O(n). It's linear. Any questions? Does it make sense? Nice. And the sliding window is also very similar to the technique in some sense. Let's talk about that. So in a sliding window strategy, yes, the brute force is O n square, and instead we can just, for example, sort it out and log n, right? Or if it's already sorted. And then just do on 2 pointers. But then of course, like we can have another, like even faster approach without sorting. Like if it's not sorted, there's not really much point of doing like 2 pointers. We can just, like, for example, do like unordered map, and then just go through the whole like array once, and then check like if in a map we have like x minus ai, as for example, like we just go through the thing. If it's not sorted, right, we can just have like unordered map m, and then we, like, every single part we just check if m x minus ai is equal to, for example, 1, so we found the answer. And then after we check, we set ai, sorry, m ai equals to 1. But this is a different thing. It's not, like, it doesn't mean that, for example, if it's not sorted, the best approach is this, right? It's just a way to show the 2 pointers topic. And then in case of sliding window, just a second. Yeah, basically we're just keeping like a window LR and sliding in through the, like, through our array, and keeping some condition true. Like, as for example, yeah, like longest window satisfying a condition. We can do it 2 ways. For example, let's say we have some condition, as for example, we need to find like the longest size of subarray, some sequence, which sum is lower than x. Like, we have some numbers here, and then we have to find the longest size for the subarray, and that the sum of the numbers in the subarray is less than x. And how we can do that is, for example, with sliding window. Like, how we do that? So, like, like the simple way to do that would be, for example, like fixing the first element, right, the start of the subarray, and then just, let's say, brute forcing through the whole array, as much as possible, as far as the, like, sum is less than x, and then trying to find the longest for each e. But for that, the complexity would be n squared, right? Because it's like four, like nested fours. And then to not do that, we can do, for example, sliding window. Basically, we can feel that, like, for example, the difference between the I minus 1 and I is just this, right? This part. And then we go through the whole thing like the same way. So what we can do is to have LR, right? Like our subarray distance, like limits. And then, for example, L is the beginning, is the start. And then we move R as much as possible. Like until some X like works. Right? And then we check this, right? And then when we reach the point of like it getting, for example, if we add this, it will like get over X. We just don't do that. And then after that, what we do is we keep the R here, and then we move L to here, which means we just remove this part, doing like sum minus equal AL. And then after we moved it, we run again the maximal error possible. Like we did this, and after it's like, well, for example, sum A R plus 1, sorry, no, sum plus is less equal X R plus, for example. We basically just move R to the right as much as possible. And then again, like hit some limit over here, stop. We got the answer for L plus 1. And then after that, we move L plus 1 to L plus 2. Again, removing this one. And then we continue moving the L as much as possible. And then we kind of keep like the window, and then we slide the window, right? LR window sliding of like this over here and then this here, both to the same direction, trying to maintain the condition true. Okay. And then we could also do another way as like instead of fixing L and then moving the R as much possible as possible, we fix R, for example, over here. And then as we add R, for example, and we get over X, we just move L as much as needed to get the sum under X again. Like just two different approaches. Like one is fixing L and then moving R as much as possible, and then one is fixing R and then moving L as much as needed, for example. Does it make sense? Nice. Let's see. But the two ways are actually the same, right? Yeah. They are the same. Like you mean for the sliding window, right? It's just two different like ways, kind of, but it's the same thing. Just fixing like different sides, but it's the same thing essentially. Yeah. So. Do you want to go through like code and then, like, for example, solve some example problem before we go further? Or we just go through the topics? We still have to cover binary search and binary search on the answer, which is like let me share the PDF. Sorry. Of course. Here we go. And then I'm also thinking on like creating a Google Sheet where I'm going to just like post the problems like listed. And then you can just like, for example, mark every single problem like green after you solve it. It's kind of like homework or something. Does it make sense? It would be nicer to, yeah, it would be nicer in terms of organizing problem set and then actually monitoring if people are working or not. So should we cover the practice problems or let's see. I have another idea. For example, if someone wants to, let's say, try to solve the problem right now, that person can share the screen and then we can just watch the person writing the code, trying to write. I don't know. If any volunteers want to try. You were given a playlist summary. For example, this problem. Anyone? Dumon, do you want to try? Solve and submit this problem. Hello? Ken, you're welcome. Try. You can share your screen. You can. It's this one if you want. Let me share it here. You can share your screen and we just watch you code.
Bro, like my coding is getting so rusty. Just take it as a simple exercise.
Yeah.
Wait, how do oh,
Yeah, like the bottom over there, like.
are you guys seeing that?
Hmm.
Let's see. Okay. All right, got it.
Yep.
Are you guys seeing it?
Yep, we do.
All right. Something. Wait, let me see where's the problem? I need to see the input and output.
Oh, I sent the code, like the link in the chat,
All right, let me see.
in the WeChat, not the Zoom chat.
The task 11:41, right?
Mm-hmm.
All right, and let's put it on my other screen. Well, it's going so slow. Does it need a VPN?
I don't know.
Can you just give me the screenshot?
Yeah, of course.
I remember, well, it's definitely got a input array, right?
Let me just share. Like,
Definitely gonna need that. Uh,
I sent you like DM.
let's call it, whatever. I'm so bad with variable names. Give me a choice here.
M.
All right, cool. Let's go. Are there multiple rounds of testings?
Yes.
So we're gonna need.
Oh no. There is no.
Oh,
It's
there's
only
no
one
right.
M.
All right, yeah. Probably gonna need a vector as well. I'll call it A, and Initialize 10. What the fuck is going on? I can't type. All right. Where's the screenshot? So n integers k1, kn, the ID of number of each son. Okay. I'm gonna start the sliding window. Or let's say it's equal to 0 as well. Guess that'll work. While r is less than or equal to. I'm gonna fix the boundaries later. Yeah, just let me know whenever I made a mistake. Just
Yeah, of course, of course.
share in chat. Yeah. Uh, we're just gonna. So it's probably gonna be if M-A. Let me see how do I frame that? M-A-L. I should push in something first, right? Okay. M-A-R. Let's say plus plus. Margin equal to 2. Uh, all right. Not too rigorous, but it might work.
Let me see. Wait.
Honestly.
So you're
And I'm gonna increment R's R and well. And I'm gonna need add one more. If this is valid, if everything's valid right now, the whole length is gonna record into one of the answers. For example, int ans equal to 0 and answer equal to max whatever ans is, and R minus L plus 1. And we'll see if that's right. You can type. Do you have the testing cases?
8, n is equal to 8, and then 1, 2, 1, 3, 2, 7, 4, 2.
Huh. Compilation error.
Return 0? I don't know. Maybe. Oh wait, unordered map.
What is that? Unordered map? Unordered map. Oh, I had to initiate it with something. All right,
Oh yeah.
just gonna do it right here.
No, like you have to the
Ah,
type of the map.
oh shit. Forgot. Haven't been writing code for such a long time, my bad.
It's okay.
Compilation is taking so long. Okay, so 8, 1, 2, 1, 3, 2, 7, 4, 2. No, it's wrong. Right. It's probably something's going on right here. Let's see what is the issue?
So basically
Yo,
here
let Leo show it. Just Leo show his code. He's already done.
that's okay. Let's us to let's say debug your code.
All right, let's try to debug my code. Oh, it's gonna take quite a while. I'm so
No,
bad at
that's
these
okay. That's okay. That's
conditions,
okay. That's
bro.
okay. That's okay. That's okay. So basically, you're like adding the R, right?
Yeah, I'm adding the R.
And if you like encounter a case of R being, let's say, more equal than 2, right? So you got like let's say like repeating, right?
Yeah, R. Yeah, I found the problem too. Yeah, like Leo said, he's right.
Yeah, but that's not only the problem.
Well, I think it is. Wait, is it? Oh, I think it is. I think it might be.
You can try.
Let me try. There we go.
You can
There
try.
you go. But I don't know if that's gonna be an accepting answer, but it's somewhere close.
You can try. You can try.
I cannot open the website, bro.
Oh fuck. Okay.
I need someone to submit it for me. But well, I mean, it's good enough for a demonstration.
You can just copy paste the code, for example, to me, and then I'll just submit.
Yeah, I can copy paste it. All right, let's move on. If everybody understand what's going on here.
I mean, let's try if it gets accepted first. Just a second.
All right, are we good?
Just a second. I have to paste the code into a file.
Yeah. And it's just such an easy program, but
Just a second.
KI is to okay. Yeah, but I think that's correct. All right, okay. One minor issue. I think it should be a while here.
Yeah.
Yeah, it should be a while here.
Yeah, that's what I was trying to say.
Yeah, this one should be right.
Wait.
Unordered map is a dictionary in Python. They're almost equivalent,
Yep.
but not under the hood. I mean, under the hood, unordered map is a little bit more. I don't know. So what's the right word to put it? Like maybe Python dictionary is harder to hack than an unordered map.
Really?
I gotta ask Leo for that. He hacks a lot of people.
Python map. Maybe. But Python dictionary is hackable.
Oh, Python dictionary is hackable? Okay.
Sure. It's very easy to hack.
Yeah. So they're all hackable.
On our map, it's
Or it's just
hackable.
code, sorry.
You can make it unhackable, but it's still very slow.
Or any questions about my code, about my problem?
AC,
It's an AC code.
this code AC.
I don't know. Let's see. What does it say?
Submit the code. Submit it.
Let's see. Pending testing ready. Oh, time limit exceeded in one test case. Hello.
What?
Time limit.
A time limit?
Yeah, one
Okay.
test out of 21 tests.
What?
Basically,
No way, bro. Oh shit! You're right. Wait, no. It should not be the issue. Is that an issue?
it's I don't know. Low possibility because the input is not that big.
Yeah, the input's not that big. I don't know. It should not be the issue. Number of. Oh yeah, it might be. It might be because it's 9 digits for each number. All right, try this one. Try this one. Integers. That's correct. That was correct. That was correct. That was also correct.
Just a second. No, time limit.
Still time limit.
Yeah, I think it's something has like have to do
Something to
about
do over
L
here.
and R. Let me see. So
Oh, I think it should be smaller than R or something. Replace the map with array? No, because the number range is 10 to the 9, and that's too large for an array. Check out the conditions here. Do you think the condition is right? All right, is that equal to 2? I'm just gonna move L to the right and just increment L. And when it ends is when L is equal to R. So I think this one might be the issue. It's a little bit an issue. Oh, I hate these.
yeah, should
Hate these edge cases, bro.
let's try again.
Yeah, that's why nobody let me code during actual competitions. I'm only in charge of thinking stuff. Yo, if I did a time limit exceed even with the unordered map, I think using map won't do any good because maps are supposed to work a little bit more slowly than
Interesting. Still time limit.
the time limit.
Mm-hmm.
Maybe it's a hack. God damn, it's crazy. Oh yeah, it might be a hack. True, it might be a hack. He's got a point. We're gonna try to turn it into a map.
Yeah,
I don't know, we can move on if you want. I don't
no,
really
no, that's
care.
fine. That's fine. That's fine. That's fine.
Yo, if you want to move on, just send in the chat.
Let me just a second. Uh, Accepted.
Accept it?
Yep.
Yo, nice. All right, it is a hack. Then it is a hack.
Mm-hmm.
Damn, it's crazy. All right. Good job, good job. Thanks for
Another implementation would be maybe using like a set, in terms of just I
like
don't know.
set
Let me think.
this set.
Okay, never mind. Never mind. Like again, map is good. Map is good. Never mind. Yeah.
Oh, he uses set. All right, he uses set. It might be good, yeah. Because if that's the set, then you just have to find if it's in the set. So in terms of this one over here, if I want to use set, if I want to use set here, just gonna change this one into something like s dot find or s dot count a to the r equal to 1 or something. Yeah, set is not faster. It's set is supposed to be log n, like each time it searches for stuff. But it's more secure in terms of being hacked.
I mean, map is also fine in terms of being hacked, but
Yeah,
like
map is yeah, true.
yeah, I think the problem with the unordered map was just like because it was overloaded, let's say.
Yeah.
Because when you let's say put many stuff,
Too many cache miss or it's like
yeah.
collisions. Yeah, too much collisions.
Mm-hmm.
All right, that's it. That's it. Thanks, guys. Thanks,
Yep.
guys.
Thank
Yep.
you. Let's continue. um, so here, let's say, boo, 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 boo. Just a second. The zoom icon is like blocking me from whatever. Which one is this? So let's see. And the next thing is going to be the binary search. So binary search finds a value in a sorted array in log n by repeatedly having the search range halving. And the standard library has like functions for that already, which are the lower bound and the upper bound. Like for example, if you do this, like you give the beginning, you give the end, you assume that the A is already sorted, and then you give the X, which is like the searching thing, like, and then you search the first element, like the index of the first element, that is more or equal to X, and then for the upper bound it's just greater than X without equal. You can call the function on both like vectors, array, and so on. But also knowing the implementation of like the idea of the algorithm is also very important. Let's briefly talk about binary search. As for example, we have like array, and it's sorted. Okay, if it's not sorted, let's say it's like not sorted A, and it gives X, we have to find if we have X in our array or no. You can't go faster than ON because you just have to go through the whole thing and check every single one, right? But let's say the array is sorted in increasing order, right? So the idea of binary search is, as it says, like binary, right? We are searching X in some very smart method. So let's say it's sorted, right? So if we try, like if we have like this array, it has n elements, right? Let's see what element we got over here in the middle of the array. Let's say it's mid. So in case of mid being greater than x, if it's x, right, we got our answer. If it's greater than x, in that case, if it's greater than x, right, this one, other part coming to the right of the whole array is also greater than x, right, because it's increasing. It's sorted in increasing order. So if this is greater than x, also this part is greater than x, the whole thing. So we don't really have anything to like left to search there. We already know that there is no answer over there, right? So after we see that, for example, this is greater than x, we narrow our search range to the left part, where the rest is lower or equal to x, right? And then we continue the searching over here. And then if we get, for example, like a mid lower than x, smaller than x, in that case, we know that, let's say it's the middle part, right? In that case, we know that, okay, this is lower than x, this is also lower than x, and this is also smaller than x, sorry. And also this is smaller than x, and this is smaller than x, because it's increasing order sorted array, right? So after that, we know that everything here is smaller than x, and everything to the right side is greater or equal. No, not necessarily, sorry. we can't really say that. Okay, never mind. We can't really say that like, this is, for example, smaller or equal to it. There can be also greater parts, but we for sure can say that there is no answer over here. And same here, we for sure can say that there is no answer for over here, and then we have to search the answer over here, right? So the binary search algorithm by itself says that we have the range, and what we do, we divide the range into two parts, check the middle part, and based on the middle part, if it's equal, we just solve, or otherwise, we are able to divide the search range into two parts. Not into two parts, like in the smaller part. Or this, right? Depending on what, like the answer of the comparing with. And then, because we are choosing the mid being equal to L plus R divided by 2, which is the middle of the whole array. And then choosing the either of this or this sides. Because we are choosing the middle, after each knowing part, the size gets divided by 2. Like we are narrowing the range of the search 2 times per every single comparison. And after some of the comparisons, for example, let's say we have A over here, we compare these, and let's say we get to this stage, right? And like this is the right part, this is nothing. And then let's say we compare this middle over here of this. And then this is the wrong part, and then this is the right part. And then we compare this middle, and then, I don't know, let's say this is the wrong part, this is the right part, and then so on. And then eventually we just reach like the binary way to like some smaller pieces, and then eventually we have only one element. And then we check the element. If it's equal to the x, we found the answer. If no, there is no answer. And the depth of the whole dividing part is the maximum log n. Because each time size is being equal to 2, right? And then basically if we repeat it log times, we just get 1. Does the logic make sense? Cool. Yep. So here is how we can find, for example, some element x in an array, sorted array, in only log n. Here is some implementation for the binary search. I do it a bit differently, to be honest. I'm not sure if my way is the best. But let's say we can try to practice a bit, right? For example, for this one, I don't know. Let's check the time first. We have time. Also, let me charge my laptop for a second. Sorry. Yep. So, let's see. There are N concert tickets available, each with a certain price. Then M customers arrive one after another. Each customer announces the maximum price they are willing to pay for a ticket, and after this they will get a ticket with the nearest possible price such that it does not exceed the maximum price. So we have N tickets, M customers. The price of the ticket is the maximum, let's say, price that they can pay. Here it's like the array basically, and then here there are the queries, right? Anyone wants to volunteer and try to implement the code for this?
Okay.
Okay, let me stop my share. You can share your screen.
Wait. The ticket. Wait, so means there are many more get an a 3, 8 get an 8, 3 get nothing. Okay. Arrange this. Let's let's exactly.
Yep.
So easy.
So here you used like upper bound, the like already implemented function for that, right? Yep. And then
Use monotonicity to get the largest number that is less or equal to t. Okay. And erase it.
So later on, I'll share like some problems that you can practice, guys. Like write the actual binary search, because it's important to write it because, like, the implementation might be very tricky at the very beginning. let's see. Let me share my screen. Just a second. Yep. And you can find very different implementations for binary search. As for example, like I do it like less equal, like with less equal, and then just update like ounce. So we can search like, I don't know, for example, CB algorithm or like this PDF or anything else for binary search implementations, like variations, and then just choose whatever is more comfortable. And then practice it so you can do it without any bugs. And then the more, let's say, usage for the binary search is binary search on the answer. Binary search on the answer is a technique which is like, for example, if we have some optimization problem, let's say, or I don't know, which says like what is the smallest capacity, shortest time, medium, maximum that still works, blah 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 blah, which basically is monotonic. Like it is like true, and then false, or like false, or true, true. Which means, like for example, let's say, let me try to come up with some problem, or just get the problem from here. So it says, for example, you are given an array containing n positive integers. Your task is to divide the array into k subarrays so that the maximum sum in a subarray is as small as possible, right? So does this mean like exactly k subarrays, or anyway, yes. So for example, here it says the problem says we are given an array, we have numbers inside, and then for the array it asks to divide the array into k parts, k subarrays, basically like this. Sorry, like this. We just divide it into 1, 2, 3 subarrays, right? So it has to divide it into k subarrays, like an array of n size. That the sum of the every single subarray, let's say sum 1, sum 2, and then sum k, the maximum over these sums, max of sum 1, sum 2, sum k, is the lowest. We need to like find a way to divide the array into key parts, exactly key parts, that this is the lowest. Is this statement clear? Yep. ideas how we are, like how we can do this? Duman can any ideas? No ideas? How can we solve this problem? Interesting. Looks like a DP problem. Maybe a sub that has the biggest number but the least number. It says maximum sum in a subarray is as small as possible. I didn't get the question, if it was a question. Duman, any ideas? Duman? No ideas? Okay. So the solution for this, what problem are we talking about? Sorry, I wasn't here. So, okay, let me repeat the problem real quick. Okay. So we are given an array, let's say array A with elements, size of n, and then those are like integers, like elements, numbers. And then we have to divide the array into k subarrays, but my civil subarrays. So, like for example, like if we divide the array into like 3 subarrays, it's gonna be like, for example, this, consequent subarrays. And then we have to divide the array into k parts, that every single, let's say the sum of every single subarray, the maximum sum of every single subarray is the lowest possible, like max sum 1, sum 2, sum k, like for every single subarray is the lowest. We have to find the way to divide the A into k parts, that the highest sum over the subarrays is the lowest. Sum is the basically the sum of the numbers in a subarray. So the size does equal k and k subarrays. K subarrays, but I didn't get the part of like less equal k size. Not necessarily. You can have like big subarrays which are bigger than k. As for example, let me show you. We have like a A 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And it's equal to 10. And then, for example, we have to divide it into like 3 parts, let's say. And then we can divide it like this, and this, let's say. And then here we have like 10. Or, for example, like, okay, divide to 3 parts, we have like 10. And 1, 1, 1, 1, 1, 1, 1. So we need to get like the lowest possible sum over the subarrays, right? And it's gonna be what? It's going to be, for example, this, and then this, right? And then the lowest is going to be like 11. Is it possible to get less? No, truly. So, this is the problem. Like, we have to find a way to divide the array into k parts, that the subarray, like the sum of every single subarray, the maximum sum is the lowest. We can have like maybe 3 minutes to think about the problem, and then I'll tell the solution. Okay. Exactly, but let's wait. So the allowed max sum is set to meet. What do you mean? Allowed max sum is set to meet. How can you greedy? Oh, like with the binary search? Binary search on the answer? Yeah, exactly. Yes. So the solution, only 1 minute first. Good job. Okay, never mind. So the solution is we can binary search on the answer. How? We basically, the binary search on the answer is we question what is the let's say highest, like what is the answer, like what is the max ans. By this question we are trying to, let's say, limit the possible like subarray sum, right? The sum of everything. Yeah, the sum of everything in a subarray, right? Right? As for example, like, let's say we have like a binary search on the answer, and then let's say like the answer is like ans, and then for our statement we are saying that if we divided it like this, and then like this or something, in every single subarray the sum is going to be less equal than ans, less equal than ans. Basically we are just getting the, like, we're considering the highest possible, the limit for the subarray sum. Like it can't go more than the need, like the binary search. What I'm saying is, for example, we consider L equal to 0 or something, R equal to the whole sum of every single element. Let's say total sum. Alright? And then what we do, let's say we have like mid equal to L plus R divided by 2, right? And then we say that, okay, let's check if for mid, does it like satisfy our condition? Like if the maximum for every single subarray is kept by mid, is it possible to divide into k parts? And how we do that is, after fixing the mid, we go through the array, right? Like we go through the array, and then greedy, with greedy, we just basically add as many like elements as possible into one subarray until we can, right? As for example, like let's say The same example over there. 10, 1, 1, 10, 1, 1, 1, 1, 1, 1, right? And we have to divide into keep equal to 3. And then let's say the L is equal to 0, and then 10, 11, blah, blah, blah. Basically 20, 1, 2, 3, 4, 5, 6, 7, 8. 28. R equal to 28, let's say. And then mid is equal to 14, right? Okay. Let's check if we can divide the sub. If we can divide the array into subarrays, having the mid as the maximum cap for the subarray sum. And then we have, like, for example, like 10, 1, right? 1, it's already 12. And then if we add 10, it's like over, so we don't do that. We finish with this. And then 10, 1, 1, 1, 1, right? And then it's over because the next is going to be 15. We don't want over 14, right? And then 1, 1, and then we're done. Like over, or like 1, 1, doesn't matter. And this is the third part. So what we saw is that for the highest sum, if the highest sum is 14, like if it's limited with 14, we can divide it into 3 parts, as it says, right? It satisfies, but is it the lowest? Not necessarily. And how can we check that? After we already checked this, let's say the mid LR. So if it satisfies, like if we can divide it into 3 parts with the maximum limit of the subarray being 14, we can also do that with any of the higher things, right? Because it's already optimal. Like the answer only gets worse here. Yes, exactly. If it satisfies, it will also satisfy for the bigger numbers too. And also, to mention, for example, like if it would like be like 20, not 20, but like, I don't know, 20, exactly. It's like 12, right? And then 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, suddenly we have like only 2 subarrays, right? If the limit is 20. But it also satisfies, because we can just divide it into 2 parts. And the sum is not going to get bigger out of that. It only gets like lower, right? If we divide 1 subarray into 2 subarrays, it also satisfies. So even like, for example, if we are able to divide it, like for example, into 2 parts, it's good. So yes, so for the bigger limitations, it always works. And then out of those whole things, the mid is the best because we need to like minimize the amount, right? So after that, after we saw that, okay, it's satisfied, what we do is we try another one. And here comes the binary search on the answer. So after we saw it satisfies, we try again. We do binary search on the answer. We change the R equal to mid minus 1. Right? We go to the other side, which is still unknown. Like, I don't know. We don't know if it's still possible to get any answer out of there or no, right? And then we check again. Check like mid equal to L plus R, where R is already like a new R, right? And then we do the same thing again. The same greedy. As for example, let's say, so after that it was 14, right? So R becomes 13, and then L is equal to 0, R is equal to 13, and then the mid is equal to 13 divided by 2, 6, right? And then let's say if we can divide the whole thing into k subarrays having the maximum sum equal to 6. Right? So no. It was very obvious that no, we can't, right? Because we already have like an element that is bigger than x, bigger than mid. So no. So this is impossible, right? We can't. And let's try. So the other case is that when we get that it doesn't satisfy to our condition, right? So in that case, we do the opposite. Instead of limiting it to the lower part, we limit it to the higher part, because we know that, again, like this was the range 28 and 0, right? And then here was like the 14, it satisfied, and then this part is like already gone. We already have our answer at least here. And then we look to this part, and then in this part, like the middle is like 6, right? So this part doesn't satisfy, right? So if it doesn't satisfy, the even lower parts won't satisfy either, right? So we just completely block this part too, and then we move over here. L becomes 7, R is 13. So mid equal to 7 plus 13 equal to 10. Sorry, divided by 2 equal to 10. Divided by 2 equal to 10. So in this case, let's see if we can divide it into k parts with the k limit, like the maximum limit of the sum being 10. So here it's like 10, and then we can't add anything else because it's already over the limit, so it's only one part. This is 2 parts because this one would be like 12, and then this is another part, right? And then this is another part. So we got 4. We got more than we needed, which means we didn't satisfy our condition, right? Because we need to divide into k parts. Which means it doesn't satisfy, right? So here the 10 doesn't satisfy, and then the lower parts also doesn't satisfy, and then we get like from 11 to 13, right? We check, for example, the mid equal to 13 plus 11 divided by 2 equal to 12. And then we check 12. 12 is going to be this, right? And then this, right? And then this. It satisfies. Good. So 12 is also an answer, right? So we change our answer from 14 to 12. And then we have 12 here, 12. It satisfies, and then we like also limit our range of search. It was like from 11 to 13. We satisfied 12, so 12 is gone, and also 13 is gone because 12 satisfied, and then 13 is like the right side. And then like over there only 11 is left, and then we check 11 too, and then we see that suddenly the 11 also satisfies, right? Over here, here, and then here. And then 11 was the last number. Here, after we change anything, like if we do, for example, like it's satisfied, so by the logic we have to like go to the left side, right? If it satisfies, like we block this part and then move to the left side, right? And then here in this case we just do like, for example, r equal to mid minus 1, which is like 10, right? And then here L is already equal to 11, so we just basically like this condition is gone because it's like the while condition for the binary search. And then that's it. We finished our binary search, and then we found that the 11th was the most optimal answer. And then this is also applicable for the question. It was just an example how it works, but then you do the same thing for the question. Binary search on the answer. Does it make sense? Any questions? Good. Everything clear? The month? Yep. So yeah, binary search on the answer can be very sometimes easy and then sometimes very also hard. Is it divide and conquer? Divide and conquer is a different algorithm. So no, it's not. But divide and conquer is also like related to dividing. We can cover it later on at the further more complex classes. Yeah. So very useful technique by research and answer. Is it solved deep and conquer? Where is the Google AI? Okay, I'm not going to ask my AI because I don't know what will appear. I'm not going to risk it. So, but like divide and conquer, where is the conquer? Like you divide, you don't conquer. Dili is властвуй. Где властвуй? There is no conquer. You just divide. Like in divide and conquer, you also like use the. Okay, I don't know. If it's nice to think that it's divide and conquer, you can think that it's divide. Okay. So that's it for the topics. I think I'll share the Google Sheet practice problem set so you can practice, but it will be like a bit later on because it's not ready. But so far you can open the usaco.guide, and then in usaco.guide, I mean you just like search usaco.guide binary search on the answer, for example, and then here it's in usaco silver, binary search somewhat frequent, and then you have resources if you need any more information, blah 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 blah, something, and then some examples, right? And then the problem set is the usaco problem set. Is like silver, blah blah blah, gold, platinum, like from easy to insane, and then general, like from CSES, right? Code forces, code Jeff, and so on. You can practice as much as you want, more better, and then we also have 2 pointers over here, the same thing. You have problem set, you can practice, it's very good. Just start to stall, like solve from easy to hard, insane, and yeah, that's it. Thank you very much for the class, and see you next week. If you have any questions, you don't, okay. Bye bye. Wish you a nice weekend. Bye.